Today we will be moving on to the third module, that is application of Laplace transforms. Before moving on to Laplace transform, let us see some of the basic functions. They are unit step function, unit ramp function, unit impulse function, and exponential function. There are many more functions, but these are some of the basic functions you should know. So I'll explain to you each one in detail. This is the graphical representation of u of t, and this is the mathematical representation of u of t. Unit step function is represented as u of t. Here, in this function, u of t is equal to 1 for t greater than or equal to 0. This is the time axis. For t greater than or equal to 0, the value of u of t is equal to 1. And for t less than 0, the u of t value is 0. And it is called unit step because the amplitude here it is 1. Next, ramp function. Ramp function is a linearly varying function. Here, the value of r of t varies linearly with the value of t. Therefore, we can write r of t is equal to t for t greater than or equal to 0, and r of t for t less than 0, there are no values for r of t, therefore it is equal to 0 for t less than 0. Next, impulse function. Impulse function is represented by del of t, and its value exists only at t is equal to 0. That is, its value is 1 at t is equal to 0, then it is called a unit impulse function, or otherwise it is called an impulse function. Here, for unit impulse function, we can write del of t is equal to 1 for t is equal to 0 and is equal to 0 for t not equal to 0. That is, it has value only at t is equal to 0, and at all other values of t, that value of del of t is 0. Next, exponential function. Exponential function can either be a growing function or a damped function. Growing function means e raised to at, and damped function means e raised to minus at. You can draw both and see the variation of e raised to at and e raised to minus at with respect to t. E raised to at is a growing function, and e raised to minus at is a damped, exponentially damped function. For example, if a is equal to 2, take the value of e raised to at for different values of t, that is t is equal to 1, 2, 3, 4, etc., and plot it in the graph. So you will get a exponentially increasing waveform function. And here also you can put a is equal to 2 and calculate e raised to minus at values using a calculator for different values of t. E raised to minus at is equal to for different values of t when a is equal to 2. For different values of t, and you can see the graph goes like this. Before moving on to the Laplace transform basics, we should know some more basics on the transformation of the time variables of the signals. There are three types of transformations: time shifting, time scaling, and time reversal. We shall see each in detail. If we have a signal u of t and we can draw the shifted signal u of t minus a, u of t minus a as like this, that is, the time is delayed by a units, that is, we have shifted this signal towards the right. If we have u of t plus a, u of t plus a can be written as we have to draw the signal earlier by a units, that is, we have to shift the signal right by a units. We can see this for another example. If we have such a signal, we can draw f of t minus 2 as we can shift this entire signal towards the right by 2 units. That is, this edge is at -1, therefore we have to shift it by 2 units and then towards the right. Then it will come to 0, 1. Therefore, the left end of the signal, that is -1, here will be represented like this. It will become 1, 2 and 3. That is, the point -1 has shifted to 1, the point 0 has shifted to 2, and the point 1 has shifted to 3. And this is f of t minus 2. And if we want to draw f of t plus 2, then we have to shift this signal to the left by 2 units. Then we will get it as -1, -2 and -3. That is, the position 1 has shifted by 2 units towards the left. That is 0, -1. That is, this position is aligned with this position. And 0 has become -2 and -1 has become -3. This is time shifting property. Next is time scaling property. We can scale a signal f of t as if this is the signal f of t, and this is the time axis, and this is the y-axis where f of t is the function. We can scale it as, that is, we can represent f of 2t like this. That is, we can scale it like this, then it will become -0.5 and +0.5. That is, the signal has compressed. And if we are going for if we want to represent f of t by 2, the signal f of t by 2 with respect to this f of t, we can draw it like this. This become -2, 2. That is, the signal has expanded. Okay. Likewise, for other signals, that is, for time scaling means if t becomes 2t, this got compressed. And for t by 2, the time axis got expanded. Likewise, we have to draw for other functions also. This is just an example. While doing Laplace transform, we will come across such cases sometimes. So we can apply this scaling property likewise. Next is time reversal property. If we have a signal like this, f of t, -1, 1, 2, and let the amplitude be 2. Okay. Then if we want to represent f of minus t, the function f of minus t can be represented like this. That is, we are going to reverse the time axis. The time axis is going to be flipped. That is, we can represent it like this. That is, the time axis has been flipped. Therefore, we will get f of minus t. See, this image has been flipped with respect to the t axis. Okay, that is the representation of f of minus t. Now, let us see an example with the scaling, shifting and time reversal property. This is a function x of t, and we have to find x of 3t plus 2. Okay, we have to find this function. X of t is given and we have to find x of 3t plus 2. For that, first step we have to follow is shifting. Shifting, then scaling, and then time reversal if there is. But here there is no need of time reversal. We will see in another example for time reversal. So this is the step to be followed, that is first shifting, then scaling, and then time reversal. So first we can do the shifting here. Shifting means x of t plus 2. Okay, it is 3t, but we have to do all the operations with t alone. F of t plus 2, then we have to do x of 3t plus 2. Okay, likewise. So first we can do x of t plus 2. T plus 2 means we have to shift this signal left by 2 units. Okay, that is signal left. That is, we have to bring this point 2 units this side. That is, this should come at -1. Therefore, we can draw the signal like this. This -2 and -3. Okay, this is x of t plus 2. Next step is scaling. Scaling to get x of 3t plus 2. X of 3t plus 2 can be represented like this. That is, all the numbers here are scaled by a factor of 3. This -1 by 3, -2 by 3, and -3 by 3, which is equal to -1. Okay, we will see another example. That is x of -2t minus 1, where x of t is this. With this x of t, with the same x of t, we have to find x of -2t minus 1. This is the x of t. We have to find x of -2t minus 1. Here also we have to follow the same procedure, that is shifting, scaling, and then time reversal. So first we will go for shifting. That is, first we have to find x of t minus 1. That is, we are shifting the time by -1. This x of t minus 1 means right shift by 1 unit. We have shifted this signal right by 1 unit. Next, scaling. For scaling, we have to find x of 2t minus 1. That is, scale the time by 2. On scaling it by 2, all these points will become half. That is, 1 will become 1 by 2 and 2 will become 2 by 2, which is equal to 1. Now we can go for time reversal. X of -2t minus 1. That is, the time axis has been flipped. Here we can see all the operations has been done on the t alone. Here, even if it was 3t plus 2, we have done it as t plus 2 and then 3t plus 2. Here, it was 2t minus of 2t minus 1. But first we have done the operation of t minus 1. That is, we have done the operation on t alone. Next, 2t minus 1. That is, on t alone we have scaled. Here, the -2t minus 1. That is, we have done the operation on t alone. Okay. So, these are the properties which you should know, basic properties you should know. The next class we will move on to the Laplace transform. Thank you.